So we were discussing electrical braking of motors. So obviously, if we just disconnect the supply, the motor will stop. But if some braking methods are applied, then it can be stopped quickly. And in some cases, if we have regenerative braking, then we can feedback some of the power to the supply during braking. So in case of DC motor, we will mainly discuss DC motor and induction motor. So DC motor, we can have mainly three type of braking: regenerative braking, rheostatic braking, or and plugging or reverse current braking. Now, regenerative braking, this is only possible if the load can drive the motor above its no load speed. In that case, only the motor can operate as a generator and feed the supply power back to the supply. And the generator braking torque, which is basically generating torque, the machine is operating as a generator, and it will have a braking torque. Motor will quickly brake itself. Now, say one of the example is for hoisting load when we are lowering the total full gauge. So, due to the motion is due to gravitational pull, so the speed will motor speed will increase, and at a particular point, it will become equal to the no load speed of the motor. Then after that, the motor speed will be more than the no load speed, so power will fade back to the supply, and regenerative torque is generated. It is required, otherwise the speed will become speed will go on increasing actually, because the motor torque and the load torque is acting in unison. That is then. So if we look at the characteristics, so this is the basic characteristic in the motoring region. So in the regeneration, we will have in this quadrant. So rheostatic braking of DC shunt motor. Rheostatic braking, the armature is disconnected from the supply and connected across the resistance. What happens? The armature has a huge amount of stored energy. So when it is connected across the resistance, that energy is dissipated in this resistance, external resistance. Otherwise, it will be dissipated across the rheostat armature resistance only, and it will take more time. So if we have an external resistance, the energy will be quickly dissipated and motor will quickly come to a halt. So for the equations, this V is 0. So our motor equation, if you remember, V is equal to E plus I into R. So V is 0. So E is equal to minus I into RA plus R external. RA is the armature resistance. So E is equal to K phi omega is equal to minus I RA plus R external. Now torque is K phi I. So omega is equal to this I is equal to K from this equation we can derive the speed. Omega is equal to minus T RA plus REX by K pi square. And in this case, however, remember that the field should be remain connected. because if phi becomes 0, we cannot have any induced voltage. So this is a circuit. So when running, this switch is closed on this side. So the motor will, armature will give the supply like this. Now during braking, we disconnect and connect on this side. So the armature get connected across this external resistance. So this speed versus torque relation, this is this if we plot, this is the curve. So depending on the resistance value, the time the motor will take to stop, that time of will depend. So C omega plus IR is equal to 0. C omega is the induced EMF, that was K phi omega, that proportional to omega. So C omega plus IR is equal to 0. So the torque T is equal to C into I. And torque is when in the transient condition, we should consider the inertia torque also. So torque should be equal to J d omega dt plus TL. So if we replace I from this equation, C omega bar minus C omega by R. So this equation, from this equation we get C square omega by R minus C square omega by R is equal to J d omega dt plus TL. So J d omega dt plus TL equal to C square omega by R is equal to 0. So this can be rewritten in this form: JR C square d omega dt is equal to minus TL R by C square minus omega. So this is the times constant, and this TL R by C square is del omega for the speed drop due to load. So this can be written as d omega dt plus omega by Tem equal to minus del omega by Tem from this equation. So the solution will be omega is equal to minus del omega L plus C1 e to the power minus T by Tem. Now at T is equal to 0, the motor will running at the speed omega L, so corresponding to the load. So omega L is equal to 0. Omega L is equal to T is equal to 0 minus del omega L plus C1. So C1 will be omega L plus del omega L. So your omega expression will be del omega L plus del omega L e to the power minus T by Tem. Now, if it is no load, TL is equal to 0, del omega L is equal to 0. So omega is equal to omega 0 minus T by Tem. Now, this is the curve. This is the load curve. This is for the first equation. This is the curve. It becomes 0. This side minus del omega L, and this is the no load curve. Now, actually, if the load is passive, then the curve stops here. But if the load is active, then only we can have speed in the, it will attain the speed in the reverse direction. Active load means when the load torque direction does not depend on the direction of rotation. Say, for example, the gravitational pull, it is active torque. For passive load torque, it will stop at this point. Similarly, the speed torque characteristic, if we draw, this is the normal characteristic the motor was running. So for braking, this is the characteristic. So if normally if it's a passive load, it will stop here. But if it is active load, it will go in the fourth quadrant for this corresponding to omega L, corresponding to this. So C I is equal to J d omega dt plus TL. This was our equation. So I is equal to J by C d omega dt plus IL. We will derive the expression of the current. So IL is equal to TL by C. এক মিনিট আমি একটু আসছি, একটু ওয়েট করো, বলে দিচ্ছে। So from the equation omega is equal to minus del omega L plus C1 e to the power minus T by Tm, we can get the value of d omega dt and put into this equation. Putting and simplifying, we get this is the expression of the current. Now just t equal to 0, I equal to minus I initial. So minus I initial is equal to minus J by C C1 by TEM plus IL. So your minus I initial plus IL is equal to this. So putting the current expression becomes this. Now if the load torque is active, we get curve 1. If load torque is active, this is the curve 1. If load torque is active, we get this one. If it is a passive load, it will end here. If it is active load, then it will enter this region, and this is for no load. This is the part for no load. Now if the time taken to brake the motor from omega initial to any speed omega 1 is t, then omega 1 is minus del omega L to omega initial plus del omega L plus e to the power minus T by TEM. So omega 1 plus del omega L is omega initial plus omega L, the del omega L to the power minus T by TEM. So this by this is equal to e to the power minus T by TEM. From here, T is equal to TEM log of omega initial plus omega del omega L by omega 1 plus del omega L. So knowing the this is electromechanical time constant. So we can calculate the time taken for speed change. Now Next one is the counter current braking or plugging. Here the connection is reversed. That is, initially the armature, this switch is closed here, so the armature circuit is completed like this. Armature current direction will be like this. Now when the switch is reversed, in that case it is closed on this side, so the current direction will be this. So initially the current was from here, from this point to this point, and now it is so during the counter current braking, we have changed the voltage direction, but you can see that the current direction should not change. So minus V is equal to C omega plus IR. So minus V by C is equal to omega plus I into R by C. So your torque is C into I equal to J d omega dt plus TL. So I is equal to J by C d omega dt plus TL by C. TL by C is equal to again IL. So your V minus V by C is equal to omega plus I. In I we place this value. So R by C into J by C d omega dt plus TL by C. So minus V by C is equal to omega plus JR by C square d omega dt plus TL R by C square. So VC by C minus omega is equal to minus TL R by C square. This is del omega equal to Tm d omega dt. So Tm d omega dt is equal to minus, this is omega 0, no load speed, plus TL R by C square minus omega. This is del omega L. So Tm d omega dt is equal to minus omega 0 plus del omega L minus omega. So your omega is equal to minus omega 0 del omega L plus C1 into e to the power minus T by TEM. So at T equal to 0, the omega is equal to omega L, then omega L is equal to minus omega 0 del omega L plus C1. So C1 is omega L plus omega 0 plus del omega L. So your expression of omega is omega equal to minus omega 0 plus del omega L plus del omega plus del omega L plus omega 0 plus del omega L. This also will be omega L. This is missing. E to the power minus T by T. So these are the characteristics. Now the motor is running with an active load torque. That is, the load torque does not change sign. The motor speed reversal will exceed omega 0 by the amount del omega L. That is this one, this curve. If it is active load torque, we will have the motor characteristic will be this one. If it is a passive load torque, the same curve, here it will break out and it will follow this curve. And this curve too is for the no load, no load operation. The motor is reversed without load. Omega 0 is equal to omega L, del omega L is equal to 0. Then omega equal to omega 0 plus 2 e to the power minus T by TEM, represented by curve 2. If the motor reversal occurs with passive load, then as I told there, this will be the curve 3. Then CI is now we derive the expression of the current. Ci is equal to j d omega dt plus TL. So I is j by c d omega dt plus IL. So IL is equal to TL by C. So now omega is equal to omega 0 plus TL omega L plus C1 e to the power minus T by TEM. So from here d omega dt is this expression. Substituting we get our expression from I. Now here t is equal to 0, I is equal to minus I initial. Putting we get expression of minus I initial plus I is equal to j by c c1 e to the power TEM. So these are the current expression of the current. This is for the active load dot. This is for no load, and this is for the passive load dot. Now the energy involved in transient process, lots of energy is involved. And what is the energy involved? The power drawn by the motor from the supply consists of the load torque plus the kinetic energy of rotating part, that is J d omega dt. J d omega dt was the torque into the speed. J d omega dt is the kinetic energy. And the loss of the motors. If we club the losses with load, the losses consist of R square R and the power required for the field excitation, normally small compared to the I square R loss, and it is neglected. The energy loss with this fixed loss is clubbed with the load, because that is not reflected in the electrical circuit, so it is clubbed with the load. I square loss is considered as the main loss. So the energy loss in the armature circuit during starting will be 0 to T starting I square R dt. Now the armature voltage equation must be equal to E plus IR. So if you multiply it by I, so VI equal to EI plus I square R. So your I square R is equal to VI minus EI. Now I is equal to T by C. T is equal to C into I. So I is equal to T by C. So it is V into T by C minus E into T by C. So T into V by C minus E by C. Now V by C is the no load speed. E by C is the speed under load, omega. So your T equal, now T is equal to J d omega dt. So dt is equal to J d omega by T. So your energy loss is expression was 0 to T starting. So omega initial to omega final. Then it was I square R. I square R is replaced by this expression T omega 0 minus omega, and dt by J into d omega by T. So this T will cancel out. So this will be omega initial to omega final, J omega 0 minus omega d omega. This is the energy loss. So for starting at no load, omega initial is 0 and omega final is omega 0. So for starting energy loss will be G omega 0 square by 2. Next was the DC machine braking. We say this is series motor braking. Now series motor braking, actually here it is the if the speed of the series motor increases, current and the flux decreases. Here it is not, because the field is in series with the armature, it is not possible to get an EMF greater than the terminal voltage, since there is no way of making the field current greater than the armature current. So regeneration under normal condition is not normal operation is not possible. Uh, Sometimes regeneration is done for electric traction. Their motors are actually reconnected at separately excited machine. Rheostatic braking is possible, but care should be taken to interconnect the armature winding and the field winding in such a way so as to ensure that the direction of the current in the field remain the same. Say for this, so this is a normal connection. So here, say this is positive, this is negative. So the current direction was like this. So now when your braking is connected, then if we connect like this, then what happens for the motor? This is positive, this is negative. So now this is positive, this is negative. So direction of the current will be, if we connect in this way, here the direction of the current in the field is same. Only the direction of the armature current has reversed. But if you do not, if you just connect these two terminals, then the direction of the current in the field will reverse. So we do not have a rheostatic braking. So counter current braking. So, so there is again a DPDT switch when this switch is connected on this side. In that case, we will have the motor current where it is connected like this. This is the resistance. So this is connected. Then we have the armature here. Then it is connected here. So it is connected like this. And this is the direction of field and back. Now if we connected on the lower side, then we will have this resistance, then it is connected. So now the armature current will change, direction will change, but the field direction will remain same. So this is the counter current braking. So the energy lost during starting of a series drive for the same values of inertia and static load may some limits of speed change may be greater, equal, or less than the shunt motor drive. When the average current during the transient operation condition turns out to be smaller than the motor rated current, then the motor torque is therefore less than the rated torque. The loss in the series wound motor will be greater than the shunt motor. But if the average armature current is higher than the rated current, because of shorter duration of the transient, series in motor losses will be lower than the shunt motor losses. Let us consider a problem. Say that one 220 volt DC shunt motor has an armature resistance of 0.06 ohm and with full field has an EMF of 215 volt and speed of 960 rpm. The motor is driving an overhauling load with torque of 172 Newton meter. calculate the minimum speed at which the motor can hold the load by means of regenerative braking. With the speed at which the load is balanced, the armature current is given by Ia is equal to T omega by Eb. So T into twice omega is radian per second into Eb twice by Tn 60 Eb. So putting the value twice pi, this is the value of torque in Newton meter. This is the speed in RPM. So this is Eb. So they are equal to sign. So this is Ia. So EMF induced during regenerative braking is V plus Ia Ra. So this is V plus Ia into Ra. So this is 225 volt. Flux remaining constant is proportional to omega. So omega is equal to 960 volt corresponding to 150 corresponding to 25. The speed will be 104.65 RPM. If a DC series motor is subjected to rheostatic braking against a load torque of 318.3 Newton meter, determine the value of the resistance to be connected in the motor circuit to limit the speed to 480 RPM. The total resistance of the armature and the field is 0.24 ohm, and the magnetizing curve corresponding to 900 RPM is given. Neglect the rotational losses. The input power is twice pi nt by 60. So this is 480 RPM. So twice pi 480 into torque is given 318.3 by 60. So 16,000 watt. Rotational losses are neglected. So P must be equal to EBIA at 480. So now if this is at 900 RPM, so at 480 RPM we can get the induced voltage corresponding to this. So EB2 corresponding to this field current corresponding taking proportional, we can get the value of back EMF. So EB into IARA, EB into IA will be this into the current IA. So this will be the values. So from EB into IA curve, EBIA versus IA curve, P is equal to 16,000 watt corresponds to IA is equal to 48 ampere. This curve, if we plot, this corresponding to this wattage corresponding to 48 ampere. And EB is equal to 330.3 volt. So total resistance will be EB by RA equal to 6.994 ohm. So external resistance will be this minus the armature resistance. So 6.7 ohm. To 20 volt 20 kilowatt DC shunt motor running at its latest speed of 1200 RPM is to be braked by reverse current braking. The armature resistance is 0.1 ohm. Rated efficiency is 88%. Calculate the resistance to be connected to the armature to limit the initial braking current to be twice the rated current. The initial braking torque, the torque when the speed of the motor falls to 400 RPM. Now the rated current is 20 kilowatt divided by the efficiency into the voltage. So 103.3 ampere. Rated torque is output corresponding to the 1200 RPM. So from there we get the value of the torque 159.15 Newton meter. So EB is equal to V minus IARA. This is V to 20 given. IA no RA no. So this is the value of EB. Back EMF. At the moment of braking, the voltage across the armature is equal to V plus EB. So voltage across the armature is this. So initial breaking current is twice IA. Initial breaking current is this. So the total resistance in the circuit should be this voltage by this current. So total resistance is this. So armature resistance is 0.1. So this is the value of the external resistance. Now, if we take flux as constant, so initial breaking torque will be twice the torque is proportional to armature current. So initial breaking torque will be twice into its torque value. So this is the breaking torque. EB is equal to 900. RPM is equal. Sorry, this will be 400 RPM. It will be equal to 400 RPM. This by 1200 into 400 equal to 69.894. So breaking current at 400 RPM will be V plus EB by the total resistance. So this is the current. So breaking torque will be, this is the normal torque, this is the EB at that value, and this is the breaking torque is proportional to current. So this full load torque proportional to full load current, and this is the breaking current. So taking the ratio, this is the breaking torque generated. Then we have the braking of induction motor. Induction motor also we can have counter current braking or plugging, which is done by reversing two of the terminals. Then the supply phase sequence is reversed. So we will have plugging. Now what happens during plugging? Now this was the normal characteristic the motor was following, so it was operating at this point. Now when we change the phase sequence, the characteristic will shift. Say it do not have any resistance, so this characteristic just shift on the negative side, so this will be the characteristic. So the speed cannot change instantaneously, so operating point shift from here to this characteristic here. It will follow this curve, and at this point it will stop and we have to disconnect, otherwise the motor will accelerate in the reverse direction. And if we during this reversal, if we insert resistance, the characteristics will can be shifted. Here if we can insert resistance in the rotor circuit, we can shift the characteristic from 2 or 3. This is obviously possible if we have a slip ring motor. Now, for deriving the approximate expression of the speed, now slip is equal to omega 0 plus omega. Omega is the speed, and this is omega 0 minus omega 0. So omega 0 plus omega by omega 0. Now we know T max 2T by ST by S plus S by SMT is equal to the ratio of ST and torque at start, maximum torque, and the torque as full load. Now considering that load torque is 0, so now normal torque during transient will be equal to the dynamic torque J d omega dt. So this will be equal to minus twice T max ST by S plus S by ST. So from here it is S omega 0 equal to omega 0 plus omega. So minus omega is equal to omega 0 1 minus S. So if we take differentiate d omega dt equal to omega 0 ds dt. So here we can so dt, from here we will have dt is equal to j by twice t max into d omega. In d omega replace t0, or we replace by omega 0 ds, so we will get j omega 0 twice t max st by s plus s by st into ds. Now when we are breaking, the omega initial is equal to, now sleep is normal, running sleep is very small, so corresponding to this will be almost 2, actually this point, but then negating the value, it is almost 2, and we are stopping breaking, so the final is 1. So omega initial is 2 and omega final is 1. So putting the value, we can get the value of the breaking time is equal to minus tem by 2 integral 2 to 1 st by s plus s by st ds. So this will be Tm by 2 minus st log s minus 1 by st s square 2 by 1. So changing the signs and putting the values, we will get Tm is equal to 0.345 st minus 1 by 4 st 1 minus 4. So from here we get Tbr by Tem is equal to 0.345 st square plus 0.75 by st. So differentiating and equating, so this ratio of breaking time to electromechanical time constant, that depends on value of st, or point at which the maximum torque occurs. So differentiating with respect to st and equating to 0, we get value of st for which Tbr by Tmax will be minimum. So st value for the from difference from this equation, we get st value is equal to 1.47. So Tbr by Tmax minimum will be 1.02, putting the value in the expression. So electromechanical time constant is equal to j omega 0 by Tmax. So Tmax is equal to j omega 0. So Tbr is equal to j omega 0. T effective breaking. Therefore, T effective breaking. This is from this expression. So T effective breaking is equal to j omega 0 by Tbr. So T effective breaking is j omega 0 is Tem Tmax by Tbr. So it's Tmax by Tbr ratio we can take from here. So putting these values, we have T effective breaking is equal to Tmax by 0.345 st 0.75 by st. Now st for 1.47, the Tbr by Tmax is minimum. So putting 1.47, the effect we get T effective breaking is equal to 0.98 equal to Tmax. So approximately equal to Tmax. So for constant load of TL, from these equations we can get the values of starting and breaking. Now if we for reversal, the total reversing time would be this plus this. For dynamic braking, for dynamic braking of আমি ক্লাস নিচ্ছি, একটু পর ফোন করছি। So from dynamic braking of induction motor, it is disconnected from the AC supply and connected to a DC supply through a suitable, two terminals are connected to DC supply through a suitable resistance. Now here actually if we look into the circuit, then what happens now in the if when the AC supply was given, then we were having a rotating field. So if we disconnect the AC supply, we no longer are having a rotating field. So the field, this is a DC field. So this is in a constant direction, in a particular direction. Now, so in the rotor circuit, what happened? The rotor is rotating, that field is constant, but the rotor was still rotating. So due to the rotation of the rotor, there will be a change in flux. So the frequency of the rotor can be expressed as S into F. This S is not slip, that is the proportional to the speed on lever into F. So similarly, rotor EMF is maximum at starting and is as the speed is diminishing, so the frequency also diminishes and the rotor EMF will be finally zero. So induced EMF is also S into E is the EMF of the rotor moves at synchronous speed, and so it is the S is the ratio of the speed of the rotor and the synchronous speed. Therefore, the rheostatic braking, the change in rotor EMF and the speed is similar to the motor operation. So we can, if we draw the circuit, the EMF is S into E, the frequency is SF, so this reactance is SX2 and this is R2. So in the same way, if we manipulate, we can have E and this is X2 and this is R2 by S. So if equivalence rotor circuit is equivalent to motor operation. So the only that if we plot, we will have in the third quadrant, in this will be the plot. So actually what happened, the motor was operating on this characteristic at this point. So when rheostatic braking braking is applied, it will move to this is without any resistance. So it will move to this point and travel across this curve and come to a halt at this point. So if we consider load torque is 0, then again 2 minus 2t max by st by s plus s by st is equal to j into d omega dt. So s, as I have expressed, it is the ratio of the rotor speed and the synchronous speed. So omega 0 equal ds is equal to d omega. So if you replace, the dt expression is minus j d omega 0 2t max into st by s plus s by st into ds. So from here we can have braking time equal to minus tm by 2 from s initial to s final into st by s plus s by st into ds. So if we integrate, we get this expression. Now what is the for the value of s initial and s final? We are following this curve. So S initial is this point. This was the corresponding to this point. To say that the sleep was 0.05. This point is 0.05. This point is 1. Now corresponding to this curve, this is just the reverse of this. So this point is corresponding to final and this is corresponding to initial. So that this initial is 1 and final is 0.05. So TBR is equal to putting the values is equal to this. So TBR by TEM, the ratio is 6xt square plus 1 by 4st. So from here, again differentiating with respect to st and equating to 0, we get xt is equal to 0.407. 0.407. So this is the value for which while the motoring, the stator and rotor EMF rotate in the same direction as the synchronous speed. If the AC speed is disconnected and the DC is supplied. So this is the one I have already explained. Now the braking torque is given by approximately 3 by omega s I2 square R2 dashed by I2 dash square R2 dashed by s, negative the stator impedance. Okay. So for putting the instead of I2, if it replaces by I1. This I1 is shared between XM and R2 dashed by S. So from the parallel circuit, we can get this expression. So I1 corresponding to equivalent AC, which would have produced the same MMF as that of the actual DC carried by the stator winding. Differentiating TB with respect to S and equating to 0, we get this expression has been differentiated and equated to 0. So we get this expression. So S is equal to R2 dash by XM plus X2 dashed. So TB max, putting the values, TB max value will be this. That is 3 by omega S I1 square XM square by 2 into XM plus X2 dashed. Now omega R is equal to S into omega S. This is capital S, which is the ratio of the rotor speed and the synchronous speed. Now as S is equal to 1, R2 dashed by S is very less than X. This is the explanation of this characteristic that at S is equal to 1, R2 dash by S is very less. So torque is proportional to 1 by S and S is equal to almost equal to 0. R2 dash by S is greater than this. So it is proportional to S. So in this region it is inversely proportional. In this region it is proportional to S. So this is just similar to the motor circuit, but in this second port. With increase in rotor resistance, the speed at the maximum braking torque occurs increases, but the magnitude of the braking torque will not be fixed. The method is convenient and used for active load. It ensures complete and effective control. If complete corresponding to the speed of operation I1 or R2 or both are adjusted to maintain the necessary braking torque. Now there are, however, different ways the DC can be applied. That is, say if the motor is star connected, then DC can be applied between any two terminals, or it can be applied like this. The two can be shorted and DC can be applied in between this. If it is a delta connected, DC can be applied across like this. That is applied across this and parallel to this. Or one phase can be shorted and DC can be applied to this. Now, what is the effect? To determine the magnitude of the torque developed depend on the connection of the DC. So in order to determine the breaking torque corresponding to different speed, it is necessary to find the equivalent AC excitation. Now for connection in this connection, for connection A, phase A and B carry equal direct current but in opposite direction. That is, this phase is not current, so it is this. So the current in these two phases are same but in the opposite direction. So if we consider the MMF, so say this is phase A, phase B, phase C. So this is phase A, B, C. So this is negative and this is positive. So resultant will be this one. So resultant will be, if the current is IDC, twice IDC n effective cos of 30 degree. So √3 IDC n effective. MMF due to IAC RMS following in any or in all the three phases will be 3/2 √2 IAC n effective. So √3 IDC n effective is equal to 3/2 √2 IAC n effective, or IAC is equal to √2/3 IDC. PDC is equal to IDC square R1. Therefore, R1 is the zeta resistance per phase. So power is VDC into IDC. So twice R1 IDC square equal to 3 R1 IAC square. Now for the other equivalent circuit, for the first one, this is the equivalent AC. This is the DC excitation, and this is the different values. These mathematical calculations, I'm not going into details, just for your reference. If anyone is interested, can consult the book. Even in detailed connection calculations given in. Now the energy loss under transient condition in induction motor drives. Now energy loss due to stator and rotor copper loss of an induction motor during starting is normally fixed losses are constant, that is clubbed with the load. So mainly what will vary is the rotor copper losses. So the energy loss will be 0 to T starting 3 I1 square R1. This is the stator copper loss. This is the rotor copper loss. Neglecting no load current, if we neglect, then I1 and I2 dash are equal. So this will be approximately 0 to T starting 3 into R1 plus R2 dash into I2 dash square. So if TL is equal to 0, T is equal to J d omega dt. Omega is equal to 1 minus S into omega S. So d omega dt is equal to minus omega S ds dt. So your torque is minus J omega S ds dt. So dt is minus J omega S by T ds. Now the air gap power is 3 I2 square R2 dashed by S. So this is omega S into T. So omega S Ts into S is equal to 3 I1 square R1 I2 dash square R2 dash. So your power loss will be minus 3 R1 plus R2 dash I2 dash square J d omega S by T ds. So if we, this was S initial to S final, this limits are changed, S final to S initial. This is rearranged, R2 dash has been taken out. So this is proportional to the torque. T. So from here we will get S final to S initial R1 by R2 dash plus 1 J omega S square. From here this T will cancel out, so this will J omega S square S into Ts. Now S initial is equal to 1 for the second quadrant circuit. Say S initial is 1 and S final is approximately 0 because the normal running speed is very small, so negative we can consider 0. So putting the values we get the total power loss can be expressed is here. So J omega square by 2 represents the loss in rotor circuit equal to the amount of kinetic energy stored in the motor, while J omega is R1 by R2 dash represent the motor stator loss during starting. Now the energy loss during countercurrent braking is determined by S initial from 2 to 1, that initial is 2 and the final is 1. So putting the values we get energy loss, this value. So energy loss during reversal with load will be energy loss for countercurrent braking plus energy loss during starting. So this is the energy loss for reversal. The energy loss during countercurrent braking is determined by the amount of kinetic energy stored in the moment of braking, the moment the braking is initiated. So it will depend on the point at which the braking is initiated. I will stop here today. I will have the next class on next Tuesday, not Thursday. We will have next class on Tuesday. Okay.
Okay, ma'am.